Alright, we're going to be looking in this video about the Vsepr theory. And before we really get started, I just want to mention that we will be practicing with this for a few days. So please don't panic. This is kind of an introduction, I guess, to Vsepr. We will practice it quite a bit to get you feeling more comfortable with it. So with that, this is kind of an introduction to it. So if there's parts that go a little quickly, I apologize for that. I just don't want the video to take an incredibly long amount of time, since this is something we are going to practice quite a bit in class. Alright, so with that said, Vsepr stands for Valence Shell Electron Pair Repulsion Theory. And since scientists love to cut stuff down because that is a mouthful, Vsepr. So what this says is that there is repulsion between electron pairs. We have drawn many times, for instance, oxygen with hydrogen attached, water, and we have these pairs of electrons. Well, electrons are negative, and when electrons get too close to each other, they repel each other, just like Rutherford's gold theory, or gold foil experiment, where the positives repelled each other. So negatives kind of work the same way. And so what happens is that these electrons, because they're repelling each other, they are going to want to be as far apart, far away from each other as they possibly can, but be with the atom that they're supposed to be around. So we have this whole group of chemistry here that kind of looks at these angles. What's the angle of all these different atoms so that we can have these electrons being the furthest distance away from each other as we can. And this only happens because molecules are three-dimensional. We get in such a habit of writing things down on paper and it looks flat. But molecules are not flat. They are three-dimensional, so we need to keep that in mind, especially when we're looking at these angles. First one I want to take a look at, just to kind of introduce you to this, is methane. Now when we're doing any of these, we definitely need to know the valence electrons, and we need to do these dot diagrams. So really quick, I want to just do a quick one here, that carbon has 4 valence electrons and hydrogen each has 1, but there's 4 of them in the problem. And so total, we are looking at 4 carbons, 4 valence electrons from our hydrogens, so we have 8 valence electrons total in methane, CH4. So what that would look like is you would have carbon with these hydrogens surrounding it, and each hydrogen has 1, and because we know it's covalent, they're going to be sharing 1 with carbon. And if we do that, we have the 4 around carbon and the 1 from each hydrogen, which gives us 2, 4, 6, 8 total electrons. And that's what methane would look like. And then what we're going to do is we need to get out that sheet that I gave you, which has all the different shapes on it. And if you take a look at the number of electron pairs, there's a pair here. This is pair number 2, pair number 3, pair number 4. You are at a shape of a tetrahedral, and so methane is going to have a tetrahedral shape. What I have drawn here with the dots, I've just kind of taken those dots and made them into the really long dash marks here to represent methane. But again, this is flat, this is two-dimensional. It doesn't really show you much about shape. What methane really looks like is this, and so you kind of see that you have a hydrogen pointing out, up, a little bit back, kind of forward, whatever. Each of these angles is roughly about 109.5, so that each of them are kind of equal distance away from each other. Now, when you have unshared pairs of electrons, those can also help predict the shape that we have. The unshared electrons are going to be held really close because they're not technically bonded with anything. So they're going to be held closer than these bonded electrons. And they have a very strong repulsion. And so they're going to push everything else a little bit further together so that they can have a little bit more room. And that's going to create some different shapes for us, again, because of those angles. So let's take a look of something that has at least 1 electron pair. Now, again, this is what the dot structure would look like, and we get these dots because of the valence electrons. Nitrogen has 5, hydrogens each have 1, but you have 3 of them. So 5 plus the 3 give you 8, and we have 1, 2, 3, 4, 5, 6, and then 7, 8. So this would be an unshared or a lone pair. These are involved in the bonds. these electrons are involved in the bond between the nitrogen and the hydrogen, but these two electrons are not, and so they are going to want to push the hydrogens a little bit further away from itself so that it can have a little bit more room. So what that's going to look like is more of a pyramidal shape. If you take a look at the paper that I gave you, there are a total of only there are 4 pairs of electrons. 3 are in bonds, but 1 un, so there are still 4 pairs of electrons. So its normal electron geometry would be tetrahedral. But if you take a look at your paper, there are 3 bonded pairs and 1 that is in one pair that's not bonded with anything, and so that's where we get the pyramid shape, the pyramidal shape. And that is going to have a slightly different angle to it. So our last one with the 4 was about 109.5, but you can see this is only 107. So in other words, these electrons are forcing your hydrogens to kind of squeeze together just a little bit more so that they can have a little bit more room for themselves. Water is another one. If we take a look at water, it has a bent shape. This is the electron configuration here so that we get in all of our electrons. And so these large red structures here represent the lone pairs. So we have 2 lone pairs on oxygen, 2 that are not bonded with anything. And so those really push together the hydrogens because those, again, want to take up more room for themselves. And because they push the hydrogens together even more, we get what we call a bent shape. Angle-wise, we could look at what that angle is, but that's really not important for the test or anything. Again, we're going to practice more about these in class as well. Let's take a look at one more, and then we'll call this introduction good. Carbon dioxide. This one has a total of 16 electrons around it, and so if you take a look, it has to have 2 double bonds actually. We have 2, 4 on each oxygen. So that is 8, and then every single bond represents 2 electrons. So we have 8, and then 9, 10, 11, 12, 13, 14, 15, 16. So there's our 16 valence electrons, and these each only represent one kind of, they're not one pair, but as far as they're only bonded to one other element. So even though each bond is a pair of electrons, since we have carbon going to this oxygen, that's once, and carbon to this oxygen, that's once. So if you take a look at that paper that I gave you, the number of electron pairs, we're really only going to be going with 2 because we only have the carbon bonded twice. Even though it's a double bond, it's still a bond of some type. How's that? So there's 2 bonds of some type, and then we get this linear shape for carbon dioxide because of that. And in this case, your angle is actually 180 degrees, so it is very flat, very linear. And again, that has to do with just the way those electrons are going to want to be repulsed from each other with these double bonds. So that's kind of our introduction. The sheet that I gave you that has all of the electron geometry shapes on it is definitely going to be a must for class for the next several days as we practice these, and we'll practice with that sheet a lot. And we'll actually look at, I think, at least an example of every single type by the time that we're done so that you can see more how to use this.